Hi everybody. Today's lesson is about Faraday's law. Now Michael Faraday, he came up with a law to find out about the size of the induced voltage. So the induced voltage is also referred to as induced EMF. And what Michael Faraday said was that the size of the induced voltage depends on how quickly the flux is changing. It's not enough to just change flux. Yes, you will get an induced voltage, but if the flux changes really quickly, then you're going to get a bigger induced voltage. So according to Faraday, he said that the size of the induced EMF depends on the rate of change of flux. Now there are two symbols for induced EMF. So it could be V, capital V for induced voltage, or it could also be this. Now the change in flux is given by that symbol, and the rate of change will mean divided by T. And then there's a negative sign in honor of Lenz to say that it's whenever flux changes, there will be an opposing voltage to show that it acts in the opposite direction. So that's just for Lenz's law. Now, because flux is equal to, since your flux is equal to B times A, where B is flux density and A is the area, the same thing can be written as, now usually the magnetic field strength doesn't change, so it can be B delta A over T, or if you're changing the magnetic field strength but keeping the area the same, then that'll be the same, but that could change. Okay, so there are different ways of writing the same formula. Now it can also be shown that this formula, rate of change of flux, is exactly the same as what you learned last year, that V equals BVL, and I'm just going to show you that the two are actually the same. Okay. So if you have a magnetic field, so this is a field going into the page, and you have a rod that is being moved through the magnetic field, not just a rod, it could be a coil of wire. So let's say you've got a coil, okay, and the length of this, that's L, and let's say with time, so it started off here and with time it moves this distance D. So in a period of time, so the coil is entering this magnetic field, and so according to the amount of flux that's changing is the magnetic field strength times the area. So the area is given by length times this distance. Okay, and the rate, so that's your change in flux, and the rate of change in flux is given by B times L times D. So I'll just remove the multiplication sign. So divided by T. Now we can see, so that's the rate of change of flux, okay? So that's B times the area divided by T. But we know that distance over time is speed. So this induced voltage, which is the same as the rate of change of flux, is also the same as BLV, which is the same as what you learned in year 12. So actually, essentially, they're both the same formulae. Now, the other thing is, when this coil is fully in the magnetic field, it's just entering the magnetic field, you know that there's no voltage induced like last time's lesson, and you will find that because the area of the coil within the field is not changing, so it's only when it's either entering or leaving the field that the area of the coil is changing, and that's the only time that voltage is induced. But in a generator, what actually happens is that you don't have the coil moving in and out of the magnetic field. So that's not possible to be done, or that's not really practical. But what you do have is a coil that's spinning in a magnetic field. So when a coil is spinning in a magnetic field, what happens is the area of the coil, which is perpendicular to the field, is changing the whole time. So that's where we come into the generator. So for a coil that's spinning in between the two poles of a magnet, what actually changes is the area of the coil, okay, with in relation to the lines of flux. So when it is perpendicular, when the lines of flux are cutting the sides of the coil in a perpendicular fashion, then you have maximum voltage generated, okay? And then it's not as much, where it's zero when they are all parallel to each other, when the movement of the coil is parallel to the lines of the flux. And we'll do that in a second video, and I hope this made sense so far. So bye for now.